Hello, everybody. Sorry, we're going straight away into the next talk. Find your spot. So in this talk, we'll diverge a little bit towards more technical stuff, but without forgetting about being human. I will talk about demystifying ray tracing. Every word is chosen for a purpose. I like to demystify things, like last year I was talking about Vulkan in general, because things are complex but can be decomposed and explained in simpler ways. So that's what I would like to do. Why ray tracing? Ray tracing because it's one of the latest technology used, still not broadly used in AAA games. We will see why it's still not widely used. But I would like you to have a grasp of the term and a mental picture of what we are trying to do with ray tracing. And that's my goal for today. So the quick agenda will be to have an introduction, objectives, going through ray tracing basics so you can have a mental model of what we're talking about, a glimpse into the Vulkan implementation, and then a use case. And then hopefully I'll show you a video of the demo that I will release next week on GitHub with a full working demo, Vulkan HLSL. Who am I? This could be a philosophical question. You can see some numbers there. I actually took a software engineering degree here in Roma 3, so I'm very happy. Currently, I'm consulting for AAA rendering, previously working multiplayer group. You can read this. I'm very lucky to have worked on these games, but I'm also passionate about both rendering and humans. So I'm very happy also about the conference and the previous presentation as well, but not only, because in this age of really AI and agents, our superpower is to remember about the humans. So, for example, right now I'm a little tense, more than probably you can feel, and it's good because I care. But I cannot just like fake that I'm not tense. And talking about these kind of things, it gives an emotional context. And I really feel that feeling ourselves, talking about our internal world is a superpower. I will not talk about psychotherapy, meditation, internal family system, EMDR, or stuff like that. But it's good to know thyself, how you learn, in which way you can process information. For example, for me, I'm really understand things if I reinvent the wheel. If I reinvent the wheel, I understand because I have a way of working that it's weird. I'm a programmer with a very gut feeling when I need to solve things. And I spend more time explaining with the head why I found the solution compared to how fast I find the solution. And I work in this way, and it's just me. It's like knowing your character RPG status, right? Okay, I'm not the best rendering programmer at all, but I have some human skills that are probably on a higher level than my technical. So if I know that, I can deliver more because that's who I am. So know yourself. It's a very, very powerful statement. So second edition of this amazing conference. And I wanted to give my contribution again on ray tracing. I worked on some project that had ray tracing, and so I wanted to recreate something that I saw on the project. We'll see an ambient occlusion. But I would like, again, to give you a mental model of ray tracing so that the words are not just like ray tracing, but it is a concept that you really mentally see. Because at the end, words are superpower again, something really powerful. So we'll see the core ideas, implementation, and these slides maybe should be, think about words. But when we talk about ray tracing, of course, now we're talking English. If you translate in Italian, it's better, or in your native language. Ray tracing, it's very simple. We are tracing a ray. What does it mean? We go to the basics, actually, interestingly enough. Albrecht Dürer, sorry, German people for my pronunciation, in the 16th century did this device in which he was having basically a grid, you can see on the right, and was using a physical thread to try to create the outline of an object on an image plane. Okay, so if you think ray tracing, you can think of the thread starting from the image plane. Okay, ray tracing. That's it, guys. That's really what it is, ray tracing. And Dürer was an incredible painter, printmaker, and theorist, Renaissance man, and actually also rasterization follows similar principles. So he was one that already theorized and used what we use for rendering in 500 years ago. But please take this picture as really what it is, ray tracing. It's threads, literal threads that are shooting in the world and telling you, hey, I touch an object here with this distance and this orientation, okay? I put a lute because I'm half musician, so I have to put something that represents me also internally. In the field of computer graphics, the first ray trace image comes from 1968 by Arthur Appel. I don't know the pronunciation, so sorry again. And it did the first rendered image with something called primary rays. Again, words. We'll see what does it mean. Actually, the thread that comes from there, that's a primary ray. So it's the first ray that you shoot. Okay, picture this always. In like 11 years later, Turner Whitted, again, pronunciation, sorry, at Bell Labs, starting to actually create the first images with more than primary rays. Normally they will use some functions that were describing like spheres and whatever to generate the images. And in most recent years, movies like Pixar, DreamWorks, and other were based on this combination of ray tracing and multiple rays. The adoption is pretty recent, actually 2018. Before we were doing something in software, but it was too slow. It is still too slow, but it's becoming an industry standard. So knowing about ray tracing is pretty important. Let's see the basic principle. So again, ray tracing. As you see, as you can see, the image plane, the viewing plane is exactly like Dürer was doing. And we are the eye point or the camera, and we shoot rays to gather information about a scene, 3D representation of what we want to see. When we talk about primary rays, as we already said, these are the rays coming from the eye to the scene. But then the rays bounce because we're actually simulating how photons work in an opposite direction, but that's another story. And then we have secondary rays. So after the first bounce, whatever is bouncing is considered a secondary ray. And normally we have three phenomena that are like shadows, reflections, and occlusion. In modern engines, AAA engines, we tend to separate the primary rays and the secondary rays because it's very costly. But again, going back to our friend here, the primary ray is that one, the thread. When it touches the lute and bounces around, that's the secondary ray. Okay. An important distinction to do is sometimes we use the terminology like forward and backward ray tracing. That's misleading because reality works, our representation of reality works by photons that are shoot from lights, and then they excite the matter and bounce back. And this brings colors. And some people were saying, okay, forward ray tracing is when I shoot a ray from me to the scene and someone knows. It's like how the rays work. So it's very confusing. So we decided to choose a different naming, eye-based, so shooting rays from me, and light-based from the light. In real-time rendering, we're doing eye-based. I will not talk about path tracing or more advanced stuff because it's still not real-time, and I would like to give you a glimpse of what we can start using in engine right now and what next games are already implementing behind the scenes. And how How was this possible? Again, until 2018, you were needing a very either specialized hardware or doing some software ray tracing. It was pretty slow. In 2018, NVIDIA came up with this architecture called Turing, by Alan Turing, of course, and they added both tensor cores for neural rendering or whatever, neural networks, and ray tracing cores. Ray tracing cores, basically, and again, core, we're talking about hardware, GPU. It's a piece of hardware that helps ray tracing, okay? And there's a new term here that's BVH, bounding volume hierarchy. Again, guys, words, bounding, so an encapsulation, volume, so 3D, hierarchy, so it can be a box inside a box. So imagine that I want to put like 4 chairs inside a box, a card box, because I'm moving to, I don't know, Sicily, because it's beautiful. And then I put those 4 boxes inside another box. This is a hierarchy of bounding volumes. Okay. Anyway, the NVIDIA decided to put some hardware to actually accelerate this so that they could be used in real time. And this became what we have right now. So there's the Turing streaming multiprocessor, whatever. That is hardware part. And then there's the software part is shaders. Shaders are GPU program, a misleading name. If you don't do rendering, you think shading as coloring, but they are just program executed on GPU, so programs. And in the hardware, it actually accelerates the question of ray tracing. So if I shoot array, what am I intersecting? What am I touching? What information can I gather from this? So actually, the hardware is doing this acceleration. So as you see, the boxes, so our cardboard boxes. For example, if I'm shooting array, imagine Albert do that, and the box that contains the other boxes with the chairs inside doesn't touch the box at all. I know that I didn't touch anything in the scene, so I miss completely the meshes or whatever. And with the second hierarchy, you can be a little bit more granular, okay? That's what does. Ray triangle, okay? As you know, maybe not, but we represent 3D objects in computer graphics as triangle meshes. And the bounding boxes are an approximation, of course. So if you want to be very specific, then you can go to a triangle level. So yeah, box and triangles. And that's what actually, it evaluates the box intersection, and then it tells you like if there's a triangle intersection. So again, let's go back and see our primary rays, the fact that we are shooting rays and gathering information. Remember this information as well. Little glimpse of Vulkan, demystification number 1. Bounding volume, hierarchy, acceleration structure. You see these big names because we were like to really try to describe things, but the concept here is these boxes, it is slow to just say, hey, where is the box? Did I intersect the box? So the acceleration structure, again, words, it's a data structure that accelerates the query, so the tracing, okay? The BVH, so the card boxes, is the way we represent the scene in ray tracing. Vulkan and DirectX, DXR, it means DirectX ray tracing, are very similar, so the concepts are the same. And we have 2 different acceleration structure. One is the bottom level acceleration structure, again, names. But the concept is basically it stores the box outside around one chair, okay? And the top level is like a scene graph, so a representation of the scene. So if I have like 4 chairs, I have like 4 boxes, okay? The combination of those 2 will give me the result of array query, okay? So if you think about this, really, we need to represent the scene with these boxes, and then shoot rays and see what I intersect, and then decide what to do with the data. That's all you need to know about ray tracing. It's called two-level acceleration structure because of these two acceleration structure, BLAS and TLAS. So again, if you read these names now, you should know more or less that what we're talking about, hopefully. This is a nice diagram showing you this. The top level is basically a scene graph, so a cyclic graph that describes the scene, and the bottom level contains the triangles of the chair in this case. So these two combined together are our acceleration structure needed to query the scene. Shaders, the GPU programs. As we are seeing from here, so we need a way to represent reality, the scene, so the acceleration structure. Then we need some shaders because we need to know what to do with the information we gather from ray tracing. And this is what the shaders does. So we have 5 types of different shaders, but we'll see here why. When I shoot a ray, I need to generate a shader. So decide where I want to shoot the ray, which direction, what am I searching in the field, you know, in the scene, using the acceleration structure, as you can see. Depending on if I hit something or not, I call different programs. I say, okay, if you hit something, call this program. If I don't hit something, call some other programs. And then there's this optional any hit intersection if we don't have acceleration any hit shader. It can be used for transparency. So maybe I hit something, but I want to know, okay, is this a texture? And there's some transparency. Okay, this is transparent here, so go ahead. The intersection shader I use more for metabolts or implicit surface. So when you don't have a geometrical representation. Okay, so every time you shoot an array, behind the scenes, Vulkan and DirectXR say, what happened here? I shoot my string, I took the loot. Did I hit the loot? No, yes, okay. I hit the loot. Where did I hit the loot? Here. Oh, what is the orientation? Oh, this one. What's the color? So you can gather information and use it. We'll see how. Again, this is what I talked about right now, intersection shader, any hit shader. And then there's this other interesting concept, very simple, shader binding table. Again, guys, sorry, BVH, SBT, it's basically a table of programs that tells you exactly this. When you hit something, call this, and when you miss something, call that. That's it. Done. Shader binding table. Like, really not happy about the interface. It's overcomplicated, but I don't know why they choose that, and it's about my pay grade, as someone say. And it's basically some handles in a table, and just like tells Vulkan and DirectXR, okay, just call this shader so you can do your custom stuff. This is some code example, but you can download the code next week so you can have a look. But there's a lot of complication for just saying call this shader. And the final step, CPU-wise, like rendering-wise, is to actually call the shaders. The ray generation, ray trace, is a command in Vulkan. As you see, there's the ray gen, miss SBT, it SBT, shader binding table. And this is the call that actually spawns the objects and save the information in a texture, like our friend Dura was doing in the image plane. For each pixel, I shoot rays, I get information. So if we want to really understand the ray tracing, the concepts are this acceleration structure, so how I represent the scene in the ray tracing world, and how I choose what to do with the data when I hit an object or miss an object. For example, missing an object could be I'm touching the sky, and so I'm adding the color of the sky. So this whole thing you can do like this. Hope it's clear. Okay, so I wanted to, that's interesting. I wanted to bring something to the table that was usable and that I didn't know enough from a ray tracing perspective. for the book, Mastering Graphics Programming. Marco did the ray tracing implementation, initial implementation, so I didn't know exactly what to do. So again, it's an interesting thing to do, to recreate the wheel. And also personally, it's a very good exercise in separating failures to personal value. Something that we are talking about quite a lot is the fact that even in the process of discovering and trying to do things, many times we fail. Or I don't know, 3 weeks ago, nothing was working with demo, and I felt very bad. I was like, wow, it's like 19 years, all these big numbers, and you cannot do the demo. But actually separating that from, and that's a normal process. You will fail, but it's not failure. You will not understand. You're missing information. You're missing something. So just continue to gather more data when you're researching something. But let's separate the personal value from what goes wrong. Because otherwise, when we're talking before, Stefano, about people that gets very mad when a texture is missing, is because you linked your personal value to that. And that's what really destroys our human component. Because before everything, we're humans. There's a human behind the role. Like there's a guy here that has a lot of people that knows and connect and loves, that cares. And then there's, all my personal story. And then there's the presentation. But I cannot just fake that I'm not a human. And again, the process of discovery means that many times you fail, but you're not a failure. There was on Zelda 2 game, for any old guys like me, a character. It was called Error. So when you were talking to him, the first thing, I was 8 years old, he would write to you, "I am Error." I was like, whoa, his name was Error. And I found really powerful metaphor to separate those two things. Anyway, ambient occlusion. I decided to dive into this poor man implementation of ray tracing ambient occlusion. It's not the best, as I am not the best rendering programmer, and I'm happy about that because I can learn more. You can find better demo around, but I don't care because the process of learning is amazing, so it's good. Again, words, ambient occlusion. Guys, occlusion means something that is hidden. And ambient, it's the ambient light, like the skylight. I hope it makes sense. But it's a way to approximate the light coming from the ambient. So not the direct light, but the photons that are like just bouncing out, like it's happening right now. This is very nice. The good people know how the math works and whatever, but the concept is just like, given a point, I look at a hemisphere, so half a sphere on top of that, and I try to pick different directions, say, hey, is this in a wood crease, or like, is there some geometry blocking the rays? If there's a lot of rays blocked, the red ones, then it means that there's not enough light reaching me, okay? This is ambient occlusion, so a way to know if a certain point is not reached by ambient light, okay? It is very important, and until 2007 it was only offline. The Pixar, DreamWorks movies, whatever. It gave a lot of, I'll show you like a picture with and without. In rendering, we tend to separate two phenomena, the direct lighting and the global illumination, the bounce lighting. The bounce lighting is what is called the ambient lighting, if you want. And without this, you will have like flat scenes when you didn't have any direct lighting. In 2007, Crytek, as some of you know, implemented the most known implementation with screen space ambient occlusion, and it led to a plethora of different techniques and evolutions. The last one is the ground truth ambient occlusion by Activision. And in 2018, when NVIDIA arrived with their Turing cores, you could finally have this in real time with a caveat. And the difference in quality is is striking. But still now, screen space ambient occlusion is used because GPUs with ray tracing are not that many or not enough. So this is a scene, old school scene, without ambient occlusion. So if you see in the shade, it's like you don't know what's happening there. Like it's nothing. It's the direct light, as you see the coming from the window, like here. It gives you information. And this, no, let's do it again. So this is without, and this is with. So as you see, the information we're gathering, especially about what's inside, is like school. It's striking. It's incredible, and this really changed how we started like doing real-time rendering. It was a, I want to say revolution, but it was a big change. And if you see again the difference with and without, so this is without, see the flatness, and this is with. You can really understand why this phenomena was implemented, and then it's still one of the most used thing in GI. The use case I wanted to bring you, it's called ray trace ambient occlusion. So we know what ray trace is, so we will use this new 500 years old technique of shooting threads through a grid, and we will see, we will gather the ambient occlusion, so how much light is not arriving to a point. Why I wanted to bring this, because ray tracing, as everything in video games, there's a lot of smoke and mirrors, and there's a lot of pros and cons. So even having ray tracing is not perfect solution at all. And one of the most fun and most difficult thing and frustrating sometimes thing in video games is that you have these amazing techniques and then they're slow. You cannot use in real time, or they're noisy, or they're not good enough, and I need to find ways around. And ray trace ambient occlusion is exactly this. How do we arrive there? Well, that's already what we're talking about. For this demo, I wanted to have something particular so that when you see the code, you can actually find a way also of using ray tracing as a first-class citizen. So normally in recent years, also thanks to Crydeck, we started like using gbuffer. So per pixel cache of information like the color, the normals, the distance of the primary rays, so the first thing we see. And so in this demo, we actually shoot rays and represent the scene and cache the depth and the normals. And as you see, this diagram in which the green is the shaders, and then the blue textures, and the red is the acceleration structure. So this is a very graphics programming thing. This is a octahedral encoding of normals. So we try to have smaller memory usage. And this is what the information basically is telling you at for each pixel which direction is facing the surface. So if you think about why do I want this direction? If you think about this, okay, the bouncing, the secondary rays, ambient occlusion is a secondary ray, so it means that it comes from bouncing. Okay, so the first step of the demo is actually to create a primary rays, and then whenever I hit something, I take the depth and the normal, so the orientation, and I can shoot another set of rays to start to gather information about ambient occlusion. Okay, so that's exactly what we're doing here. Yeah, so that's why we need normals, because they tell us the first thing I hit where the light can bounce, and that's fundamental. This is the depth, so it's the distance from the camera, view space depth, and in the closest hit shader, if you remember, when I hit something, I gather information about the triangles, the texture, whatever, and I save everything for each pixel. And at this point, we have the primary rays. So again, the thread from Dürer is there. For each pixel, we know what we hit, where we hit, and which direction the light will bounce. And at this point, we can cast our ambient occlusion rays. And again, the objective of this demo was to write something from scratch that could be easy to follow. This is the algorithm. I hope it's visible. But this is what's really happening behind the scene. As you can see, we're using ray tracing only for the ray trace ambient occlusion, the first green box. And then we use some filters because with new techniques come new problems that before you didn't have. So normally you add like some spatial filter and temporal filter. Again, names. Spatial filter is like a blur normally in texture space. So I'm doing a Gaussian blur like in Photoshop if you want. Okay. The temporal filter is something that uses information for more frames to actually get a better grasp of the information. It's actually what we do with our eyes. Okay. We get information by more frames. It's not like always 100% one frame. And this diagram shows you the general like technique, and we'll see it step by step together. So the first step is again to ray trace the secondary rays, so the one that bounces. So if you remember ambient occlusion, we need to basically do this. So in P, I touch the points on the surface, and then the normal, I take the normal, so the direction, and then I need to shoot many rays in the hemisphere to try to understand roughly how the geometry surrounding that point is occluding. Okay, that's what we're doing there in the first step. But so we're using again TLAS, the acceleration structure, so the bounding volumes and whatever, the shaders. This is the result. It's very disappointing, guys. The first time you see this, and like, well, what's this? Why is this? So ray tracing is slow. I mean, this technique in total takes 1 milliseconds on 3070 laptop GPU. It's okay, but if you're running at 60 frames per second, you have 16 milliseconds, 0.6666, the number of the beast. So you need to decide, in theory, for each pixel, you should shoot like, I don't know, 256 rays. But here we shoot one because we want to be fast. So this is the output of ray tracing AO, and it's horrible. It's like, well, how can you use this? Come on, like, are you joking? First time I implemented it, I was very disappointed. I was like, I'm doing something wrong. But then the more you understand, the more you see that the problem is not in the ray tracing, but it's called denoising, the filtering of the image. So how can we blur? How can we reuse informations? That's the biggest challenge. And that's why steel is an active field. Steel is not widely used in real-time ray tracing, in real-time rendering, not only for the GPU, but also because there's so many ways to try to improve this horrible pixely stuff. And filtering the image, again, means reusing information either from previous frames or from adjacent pixels, so that we can understand a little bit more about what's happening. And again, a spatial filter is a blur, as a temporal filter is using data from previous frame. We'll see this. So the first thing we do is actually a blur, so that if you remember I'll show you, but this picture is a little less noisy. It's a little more less pointy, if you want. Still not good enough, but it's a start. And I'm like, okay, this is a way to filter that can help, because it's the phenomenon of ambient occlusion is not very precise, so we can smarmellare, si può dire. We can do these kind of tricks. But it's still horrible, not usable. It's like, guys, no, I will never ship something like that and that games. Like they deserve something better. And then the magic comes in, temporal filtering. This is the game changer. we use more frames, and in real-time rendering, we use that for temporal anti-aliasing. It's a way of using more data from previous frames to say, okay, we're reaching the pixel or not, is occluded or not. And this is the result with the temporal. And if you think about it, it's very interesting. So we use previous frame information, and it's kind of like we're doing some sort of probabilistic function. Say, okay, I need to shoot like, I don't know how many rays, let's say 64 rays to know for each pixel, but I shoot only one. But if for 64 frames, I reuse the information, taking in consideration when the camera moves and whatever, I can sort of have an idea of what's happening, even though I shoot only one ray per frame. That's the big game changer. So you're reusing information and say, okay, if I shoot in every time in the same pixel, rays in different direction, after a while, I will have an idea that here is blocked the light compared to here. Okay, that's the idea of temporal filtering. Another big topic is noise. And it's not fun stuff, but there's different kind of noise. I also put that in the demo. One other thing is that noise just give you some random numbers so you can shoot in random direction. But there are actually some noise. So noise, random number. If you hear the word blue noise, there's a very buzzword in rendering, is a noise that is very similar to some functions of the eye, and so it gives a perception, a human perception. It's much better than the others. I'll have a video to show you later. Anyway, we're shooting these rays like in hemisphere for each pixel, and we're using, okay, more or less after 64 frames, I know that on average, half of the rays are occluded. So this would be like the around the column and the base. So, okay, I can get information. But then when you move around, you lose a lot of data. And so we apply another weighted blur in which we actually try to reconstruct if in the previous frame, the pixel we're saying in the previous frame was similar using depth and normals information. If it's similar, we can reuse. So it's like, okay, one of the pixels that is in the lion head, then I move the camera and I try to see, going back, is this still the lion head? Yes. I can reuse information. Is this the lion head? No, let's discard the information. Okay, I know as you see, there's a lot of components that are not very easy, but if you deconstruct them, they're very simple questions that you're trying to ask. It's always about questions. That's the most important thing we can do, is ask the right question. So a filter like this with this weighted Gaussian blur is like just saying, okay, I blur and try to reuse information. Is this the head still of the previous frame of the lion in this pixel? Yes, no, reuse not. Okay. And the result is, you cannot see here much, but when you're moving the camera, it's much more robust. So that's why you need two blurs. This is already something that I talked, the fact that when we're animating the noise, we get information for more frames, and that's incredible. So, for example, going back to the raw ambient occlusion, beautiful. There's a next-gen game that I'm working on. If you see, and again, I'll show you a video, but if you see the following image, you see that the rays are going different directions, but you can still sort of get a feeling of the geometry underlying. I mean, visually, you can still see where the lion head here is. So you start to understand why we need more temporal information, because we're trying to get a spatial information. And again, we're shooting rays, and more or less around the column, there'll be like occlude a lot more. And this is the kind of output that for each frame we do, and we collect data. And it's pretty trippy. But the temporal filtering is what really helps. And there's another problem is called ghosting, something that you find also in any temporal technique suffer from ghosting. So if you're not discarding, not have good criteria for discarding pixels, you can have like trails of information from other pixels that should not be there. And so you see this ghosting. It's something that if you see also in techniques like DLSS, the neural network anti-aliasing and super sampling. If you don't have a good criteria to choose if the pixel was useful, you get random data, so you really see ghost moving. So that's, again, these are all like topics that are very specific, but we always try to reuse information as more as we can. The word filtering, it's again, wording. Filtering is denoising. So we have a very noisy image, as you can see. So we're trying to remove the noise. And this is actually the most difficult thing to do in ray tracing. Ray tracing itself is easy. You just shoot the ray and you gather information. But this is the biggest topic. There's many implementations around that are much more complex, like this demo, like the SVGF denoiser. There's the spatial temporal variance guided filter. Okay, and let's do this exercise. So spatial temporal. So it means, as we did, spatial, it means getting information around the pixel. Temporal, reuse information from multiple frames. Spatial temporal. Variance guided. Variance guided means that we try to see how much of the pixels around are probably the head of the lion or not. Okay, and if they are, we can use the information. I mean, that's all that it is. Like, we like these big names, and it's a very complex way. But at the end, what we're trying to say, okay, I have a pixel. If I look around in space and time, am I still looking at the lion head, or I moved around and I don't have any more information? So even these techniques that gather a lot more data than the one I created for the demo are actually this kind of mentality. How can we reuse data? How can we reuse information? Quick do RTX. If you have an RTX card, you should. You play it. Use the SVGF. There's also some Doom 1 and Doom 2 ray tracing implementation are amazing. And depending on the different phenomena, if you remember, let's go back. If you remember about the rays, yes, here we're saying that the secondary rays are mainly reflections, shadows, and occlusion. Each of these different techniques needs different way of reusing data. So that's another like very, very, very long topic, but it's something to remember or to know if you're like working with ray tracing, that the solution I apply to ambient occlusion doesn't work for reflections at all. It's a failure. It's like, no way. So it's an active topic, and it's something that really, it's really important to know. Yeah, actually, I'll show you the demo in a bit. Again, let's do a recap, because I hope that you will. This is ray tracing, guys. This is ray tracing. So once you have a representation of the scene, you should trace and get informations. You can use it for other stuff like sound or, I don't know, AI, physics. There's many usages, and we're just starting to use that. So it's a evolving technology. Still is not a first-class citizen. There are some games that will come out in the next few years that will require GPU with the card. But really, now when you hear the word ray tracing, I want you to think about this. This is what is ray tracing. Okay, guys? This is really everything that you need to grasp. When you think about acceleration structure, it's the boxes in which we put the chair to see, hey, am I touching the box or not? It's faster mathematically to know the shape of a box compared to a chair. That's it. If you think about primary rays and secondary rays, so primary rays are the ones shoot from my point of view, and the secondary are the bouncing one. And that's really all that you should grasp in this presentation about ray tracing. Yeah, the GPU, you should have a GPU ray tracer now, like from the 20 series of the GeForce, NVIDIA, whatever. They all have ray tracing cores, but still is something evolving. Ambient occlusion, again, remember this, just like getting information about what is not visible from a point in a hemisphere. So you put a sphere, you cut in half, and you orient on the normals, and that's all you need to know. And yeah, I hope that there was some value for you and that you understand a little bit more about ray tracing. Thank you for being here. And for now, that's it. Here are some links because as you know, there's a lot of stuff to research. You cannot do it alone at all. So in the slides that you can download, you can research some of these things. Things in evolution. The demo will be available next week. So you can have like a code. I decided to use HLSL with Vulkan so that the shader can be used also with DirectX backend. So I didn't have time to create a DirectX backend, so that was my middle ground. Also with Marco Gasolina, the author of the book, well, we created a YouTube channel called Caffè con I Programmatori, Coffee with Programmers. We like to continue sharing the Demystify game dev because it's an amazing topic. I love making video games. We're creating like an engine from scratch to make a full course on that. And also there's a second edition of the book that is coming. So I didn't say anything. But yeah, any question? Now it's the time.
So thank you for the talk. There are a couple of questions.
Yeah, go ahead.
So it's like I never really delved into denoising myself. So I'm gonna ask probably stupid questions. But one thing is, what do you feed to the temporal pass? Do you feed the weighted, filtered? Okay, from
blurred. Yeah.
So for the next frame, you okay?
Yeah.
So yeah.
Yeah, so you want to give the blurred image so that is already a signal that is a little more clean, because otherwise it's too blurry. In this video, show you, we give the low quality. So this is the demo, and if you can see, it's still blurry. Notice also the edges of objects, how they can be pixely. Okay, this is still like not the best ambient occlusion at all. But yeah, you need the blurry information. Sorry, I go for the second question, but in the meantime, you can see here what's happening behind the scene without the blur.
That looks good. The other question is,
yeah,
it's always like a bit baffling how, like, how do you choose which filter to apply first? Is it like going to be spatial, temporal? Like, is there a science behind it?
No, that's the failure self-value thing I was saying. Before I was trying with the temporal and then the blur after, and it was not working. So there's a trial and error process that you need to do until you find the sweet spot. Even the error radius and the blur width, it's something that you have to try. There's still not a precise, or at least I didn't find. Let's say I didn't find a precise way. I just found something that works. But by researching, I saw that they were always giving not the raw AO of the previous frame, but the blurred AO. So that's important. And here you can see in a moment, this is very trippy. Without the temporal, this is what you see. You just like shooting rays around, like trying to get information, and then using the different. This is a frame by frame, so you can see how even changing frame, you can see the features of the scene, and you can see the different noises, how they behave. So this could be a good playground to get a grasp of this. There's an interleaved gravity noise, vocal disc noise, but the blue one is the one that gives you the eye perception. That is the best one. Yeah.
Thank you.
Yes.
You. So first of all, great talk. I have one question, probably a stupid one, even dumber than a stupid question. So first of all, you said you shoot rays from the camera point of view on the surface, and then based on the normal, you cast a certain number of rays in all directions on that semisphere to see how many of them are occluded, basically. And then I guess you apply some kind of heuristics to understand less light or more light based on how many of them are there. And my question is, what if there is a light there, like an actual source of light? So in a surface which is kind of occluded, but you have like a LED strip, for example, or something like that, how you handle this kind of situation?
Okay, so for this phenomena, the occlusion itself, we don't talk about light, we talk about the geometry. That's why it's called ambient light, because it's just about the indirect lighting. So you don't, that will be global illumination. That's a different one, okay? So we're talking about, well, the question here with ambient occlusion is like, given the geometrical surrounding of a point, is this like inside a cave or inside a grease or not? Then you can apply light, but we don't take in consideration light.
Just grab the informations and then they're used
that's why you read the depth and the normals. You don't read any light information.
Okay.
You read just the geometrical information. You want to know, again, if I'm here inside here, I will know that around this point here that you cannot see, it's light is trapped because of the geometry. So it's more like trying to understand the geometry, how much it blocks light.
Okay. And are these kind of information then used in global illumination, or?
Yes, exactly. Because global illumination is the secondary, the bouncing photons coming back, and so you use exactly only for the global illumination, use the ambient occlusion. You don't use on the direct light. That's not entirely true. There's some techniques that use an approximation of IO to help also with direct lighting, because still, if you're inside a crease and I have a torch, but you're inside a crease, I won't see anything. But the general idea is like, we're getting information about the geometry.
Okay, fair enough.
Surrounding geometry of a point.
Thank you.
Great presentation. Thank you, Gabriel. So my question is, currently we have those devices which have ray tracing cores, and they're great because we can shoot rays in a very fast way, but they are still, there's plenty of optimization that we can do in the future. So what do you foresee for the future? I mean, there will be only ray tracing, or are we going to get rid of rasterization for good, or eventually we're gonna find something which has been good using rasterization, and then we eventually set on a hybrid technique?
So this is a personal take, of course, but I see in the near future probably moving towards a full ray traced, only ray traced rendering. Rasterization, if you think even like about with complete shaders, we're ditching a lot using triangles, and internal information let me know that in the future could be a time in which we'll do mostly ray tracing and almost no rasterization. Like this demo has no rasterization apart from in GUI. The only triangles is the UI. Everything else is coming from ray tracing. Of course, you have a problem because if you have that bias, for example, you need to move the depth of a pixel. So you need to calculate that into the ray tracing. But I see a near fusion which will have like even like here ray trace pre-pass, no rasterization at all. It's a chicken egg problem because then you see hardware and drivers what is the direction, also studios wise. But as far as I see in the near future, I would say that it could be possible that would be a ray tracing only, and it would be interesting because then you need to rethink all the problems. And optimization wise is the typical, it's all in the denoising, in how you can reuse informations. So that's a very active field. You can do this ambient occlusion. I mean, it's a very, it's not precise as something like shadows or reflection. So you can do a half resolution. You can do all sort of stuff, but the denoising is really the key point here. So how can I use data? So yeah, but to me, there will be more and more ray tracing only games coming in the future. So, yeah. Yeah.
Hi. Thanks for the very interesting presentation. My question is to understand the application of ray tracing. Can I also be applied for fluid, such as water or oil, or mirror to object reflection? The for the triangles, or prefer to square the object or character?
Okay, so I lost a little bit of words there. So
Sorry.
no, it's not your fault. But so you're saying if I understand correctly, if there's can be used for something like water reflections, like water, you mean like by the surface of the water or
Yeah, the surface.
Okay, so when we saw the it's an interesting topic because there were some shaders like the intersection shaders that are used when you don't have any geometry like a triangle. Okay, so you could use that to actually simulate surface of the water and gather information about that. So you could do that. For reflections, like mirror reflections, that's already one of the things, like the reflections, the secondary rays, shadows, reflections, and ambient occlusion. So it's already one of the three things you do with ray tracing now. It's ambient occlusion, not screen space, ray trace reflections, and the shadows. So that's already doing. But it could be interesting to do some fluid dynamics and similar if you find a way to mathematically represent the geometry. Because if you don't have triangles, so even you build a mesh and you dynamically move it and you create like the water surface and then you can do it, or you can try to use the some mathematical representation. So it could be, as you see, very interesting topic, and I encourage you to try because you could discover very nice things. So still don't know anybody that was working on something like that. So yeah,
Thank you.